Okay, now we're going to go into Chapter 5 stuff. So, there's a number of things that Chapter 5 covers. Did either of you guys have a chance yet to view the video that I posted, I think, last night?
I got to watch the first 2/3 of it. I didn't have a chance to finish it, though.
Okay.
I did not start it.
Okay, was it helpful, Bryce?
Yeah, it was good.
Okay. So,
And I'm still working my way through the chapter reading-wise, too, but...
Okay, great. So, Chapter 5 has a whole ton of different things, and so the goal of this, maybe probably we won't need more than 30 minutes, just so you guys both know for time's sake. There's everything from cache and cache tags indexes to memory hierarchy to virtualization and memory virtualization, and how we can be a whole bunch of different ways to be efficient now that we have all these things to play with. Oh yeah, that was the other thing. And then I don't know why in this section, but they throw in hamming or error code and code detection and correction, and mean time to failure and average time to fail. So what I would like tonight is each of you to choose one of those areas, and I'll teach it to you right now, the skills related questions. I'm going to do the virtual memory, because it's somewhat abstract. Ironically, it's for virtualization. And then you guys can choose, though, like one of you guys, I'd really like to be the expert when we go in class and groups and teach all your peers on cache tags. That will be very important. And then maybe one on mean time to fail, availability, or hamming code. What would you like to do, Bryce and Christian?
I would be willing to do the cache tags. I remember that part from the video and stuff, so
okay,
I'd be fine with that.
Christian, would you like to do failures or hamming code, or?
I'll probably do availability.
Okay, so I'm going to give you a couple all to do, because this book groups them all together. And again, this helps prep you all, your peers, and you for CS 4200. And having taken that class a long time, a year, 2 years ago, I don't know when it was, anyways, the 5200 version of it, it's very useful that you know this, and it's useful in your career, period. All right, so let me pull up. Well, who wants to go first? I'll leave it up to you guys. Christian or Bryce? Who wants to go first?
If you're okay with me going first, just in case I know you said it'd only take about 30 minutes, but in case I do run out of time, so I have to go back to work. But,
sure. Okay.
Go ahead.
Okay, so we'll put you first in the pipeline then, Bryce. All right. So,
sounds good.
Let me pull up. Which examples do I want to go over? Let me pull the slides up first, because that's going to help Christian and make sure you and I are on the same page from what you saw on the slides. So let me ask. Okay, you ought to have gotten to here in the slideshow where we give main memory and then we dissect.
Yeah.
Okay, did this example make sense to you?
Yeah, for the most part.
Okay.
Here's thing I was
Go ahead.
I was just like, before I had to end was basically where you were saying how it goes, and I guess takes a survey of your memory and just pulls stuff in. I think, if I remember correctly,
okay,
was where I finished up.
Okay. Let's go back to here. Right. Oops. Here. Okay. So I want to advise you right now in the book, Bryce, and what your peers might ask you about is it gives an example, and in this example, the cache available has 8 blocks available. Do you see that?
Mm-hmm.
So here's main memory, right? It has 32 blocks, right? But the cache only has 8 blocks. And I want to advise you in the book, what it recommends doing is saying, oh, because it's a value of 2 to the third, because 8 can be represented as 2 to the third, that means we just keep the last 3 bits here, right? And that's our tag, right? That only works when you have an even or something that is a modulus of 2 basically. So what I really want everyone to learn in class is, regardless of if there's 8 cache blocks, 9 cache blocks, 10 cache blocks, to find out where it's going, you want to take the block address of main memory and mod it by the number of blocks in cache. Okay, so for example, right, this converts to block 5, right, 0, 1, 2, 3, 4, 5, right, and it equivalently, though it's in the 6th position, so we'd take 6 mod 8, right, and 8 doesn't go into 6 at all, so it'd go into 6th block. Okay,
6, okay,
right, so that's the location that it maps to in direct mapping. Okay,
gotcha.
and so be careful, because I'm concerned, based on the book example and the slides, that people will just think, oh, okay, so I just take the last order number of bits, that's my tag every time, and they don't realize that no, that works in this example and the book example, because this is a power 8, can be represented as a power of 2, right, 2 to the 3rd. So it's better that they learn to just do the decimal math, I think, so that they don't mess up. Okay, so that's how you That's how you calculate the index, right? Is you take the block address from main memory, mod it by the number of blocks in cache. Okay, so for example, if I'm in to check if you're understanding here, if I say find the cache index, or what blocks in cache is another way it might be phrased, would we write RAM that has a block number of 32, right? In this example, what would I do? How would I calculate out where it goes in cache if it's at block 32 in main memory?
So it would be 32 mod 8, because that's the number of blocks you have in the cache.
Great, and then whatever results, right? So what's that?
4, I think.
Yeah. So no, that's division. That's not mod.
That's just division.
I willingly went down there with the trail with you too. I'm like, yes, no, that's division, not mod.
Yes, no, not quite.
So
it'd be 0. It would go in the 0 spot.
So it's going to go in here, right? Just like 16 would map to there, just like 8 would map to there, just like 0 would map to there, right?
Yes.
So that's why we need the tag, right? So then the tag is easily calculated. The tag is just based on your system, whatever's left. So between you and me on the test, I'm probably going to give a power of 2 examples so that it helps, so they're less likely to error and it increases their understanding. But the tag is what's left, right? Because 8, 16, 0, 8, 16, and 32 all map to block 0 cache, right? Then we need the tag to know which one of these it actually is, right? That's why we need the tag.
Gotcha. Yeah.
Okay. So
yeah.
So that's direct map. That's how to calculate the block number, and the tag will be what's left of that, right? So let me go into fully associative. Oops, where is it? This is it right here. So this gets a little more abstract. It's not a huge difference, but this gives you kind of like it backwards. So if I present the skills question on the test this way, I want you to be able to, I'm going to give you an example to walk through with your peers. It'll be the part of the first one and part of this one. So for example, in this one, right, if they have 64 blocks, right, in cache, okay, and there's 16 bytes a block, right, to what block number does address 1200 map, right? Well, here's the key word, right? They say it's an address, right? So that's the key word, right? So if there's 16 bytes in a block, right, first you need to find what block it's in main memory, right? So the block, you do this to find out what block it's in main memory. Okay, so 1200 divided by 16. So now you have the block in main memory in RAM, right? Now, what block does that map to in cache? Knowing there's 64 blocks in cache, then you take that, just like I said, right? Mod 64, right? Now you know what block in cache it maps to. Okay? Does that help you a little bit?
Yeah.
Okay, now I want to make sure you emphasize to your peers right here, right, that it's got to be valid for us to reference it. If the valid bit's not set, right, because this is what it actually looks like, right, I've kind of been building, right, if the valid bit is just 0 or 1, if it's not set, what does that mean about that block in cache?
Just that it can't be. I'm trying to remember what sets that one. I know it.
Very good. No, this is
Comes
good. I'm
from-
glad I asked. This is good. I'd rather you. It's better you actually. We have to talk through this. Okay. So if it's not set, that means it's never been written. Nothing's ever been written here. So you can't just go out and grab what's
Gotcha.
there, because it's theoretically it's possible, maybe not that probable, but it's possible that the random junk that was left here last in the tag and the data or instruction, right, might match an actual tag in memory. And so without a valid bit, they might go, the search algorithm might go in here, check the tag and go, oh, it's good, it matches what I was looking for, and now I don't have to go all the way out to main memory, it's in cache already, I got it, use it, and then it's all just junk. It was random bits from whatever last used it. So the valid bit needs to be set, meaning yes, this is a valid piece of information, right? Okay, that's what
Gotcha.
that's what the valid bit is, all right? And then
And is that set? So that's set when it's pulled into the cache, and then is it changed after that so that that you're not using an invalid thing later? Is that what happens?
yes, it's set, right, when we do a read, right? So when it's pulled from main memory
Mhm.
into cache, that's a read. It might also be set on a write, because you can have a situation where you have a write miss, where the program creates something that needs to be written out to main memory, and the address has never been pulled into cache. So then you create a cache tag, you write it into cache, right, and then the valid bit's going to be set. But then this needs to now be written also out into main memory, or else you're going to have an inconsistency between your main memory and your cache, right?
Gotcha.
So those are the two cases immediately. There may be others, but that are simple and easy to talk about. Good questions. And then this is your stuff here, Christian, we'll talk about in a little bit. And then, so that was all direct mapping. Now, sets, okay, with a set, it's different, right, in that there may be a couple places to, it's like pockets versus, instead of a pocket, instead of a small amount of pockets for main memory, it's like a big pocket for each area of main memory, right? And so there's pros and cons. I talked about that in the video. But here's the math I want you to realize. I don't know if it shows it here in the... it's just the same. It's all I want to show you. It's not here. But all you're going to do to find the set, right? Let's say it's two-way set associative, right? Which set it's going to go to from main memory into cache is the same thing. You just take your main memory number of your block for main memory and mod it by the number of sets in cache, and then it's going to give you which set it belongs to. Okay, so it's very
So
similar.
memory block mod.
Go ahead.
Sorry. So main memory. Sorry, I just want to make sure I have this.
Okay.
Block modded by the number of sets.
That's right. Right, because with number of sets,
Okay.
right, it could you just have to get the correct set, and then you can put it anywhere you want in the sets, right? You can put it anywhere you want in that pocket, right? Okay, that's for
Gotcha.
part-way set associative, right? And if someone asks you, well, how do you do fully associative? That's a good question. It depends on every single architecture, because fully associative means there's no direct reference between main memory and cache. So they can take anything from main memory and put it anywhere they want in cache. There's no relative reference. So fully associative, ironically, has no reference or no association with main memory. So maybe a misnomer, but it's direct map and part-way associative, like two-way, four-way, eight-way, are where it's some relative association using the mod operator, right, from main memory to cache. Okay, whereas full associative, like in this example I go through in class, it's almost like you just treat your cache as a stack, and as you pull stuff in, you just push it into cache. Pull stuff in, push it into cache. Pull stuff in, push it into cache. And then when you're out of cache, bummer, stuff just falls out. It depends. It totally depends on the system architecture. All right. Now, modern architectures have gotten this down to a science. I've run some simulations on this before, and they've got it down to where they, in hit rates, right, and guessing what data or instructions they're going to need next, they can get over 95% correct. So 95% of the time they keep people in cache. That's pretty impressive. So only 5% of the time on average they have to actually go out to main memory or further out. So they've got this down to a pretty good science. All right. So in class, the example, I'll come up with some examples for you to go over with your peers, but basically I'm just going to grab that first one I showed you, where it's really simplified so you can explain, because this is why I like this one. It's simple, so it's a good primer. It's not completely true of all cases, but it's a good primer. So you can show them, hey, how, take block 6, mod it by 8, or take block 18, mod it by 8, whatever, right? And then so I'll give you that, okay, as a question, and then I'll give you where is it? Then I'll just need you to be sure to talk about, I'll give you this, so you have the tag, and valid bit, and then data or instructions. I wish I wouldn't say data there, but anyways, and then I'll give you the last part, right here, where I'll write it up as a question. Okay, how would I find the block number in a two-way set associative cache? Okay, and then you can help work them through that.
Gotcha.
Okay. All right. So yours, if you get it, it really isn't that hard. It's just to apply this knowledge, they really have to have an understanding. So if they're lost or they haven't watched the videos, I'm not expecting you to fill them all in on that in like 5-8 minutes. I more want you to show them the formulas and how to apply it. If they're totally lost, they need to get help or watch the video, because it's a lot of information. Okay. Any questions on that?
I don't think so. I hadn't gotten to the part yet about the set associative maps in the video, but I'll definitely try to finish that either tonight or early tomorrow, and I'll just email you if I have any clarifying questions.
Okay, that'll make a lot more sense then after you watch that, because I just very briefly went over it, so we can keep on time for Christian here. All right, Christian, let's talk about failures and performance. Oops, where is it? I think it's near the end of the presentation. So the book is kind of interesting. I don't know. I didn't write the book. I mean, I can imagine it was fun writing 700 pages of material. But they introduce this guy right here, which is important, and you're going to see this over and over again. Just FYI, Bryce, what I taught you, that same logic and algorithm and solution, you'll see that applied in other things. Okay, so it's not just explicit to cache and main memory. So same with this, Christian. This is not just explicit to hard drives that I'm going to teach you about tonight. Okay. So, Christian, are you ready?
Yeah, I'm ready.
Okay. So here are the terms. Okay. Mean time to fail. Obviously, that's focused on average time between failures. Mean time to repair is focused on how much time to get something running again, right? Mean time between failures has both time to fail and time to repair. And then availability is the ratio, right, of time to fail over mean time between failures, okay? So I'll express that, I'll expand that a little bit, so hold on. So in class and for the test, what you guys will be expected to know, let me go to chapter 5 here, hold on. And how this all fits into memory, oh, by the way, Christian, is I'm going to go over virtual memory, but what I just taught you, Bryce, right, assumes that when we pull data from the hard drive or RAM, that it always comes without any corruption. Okay, well, that's not necessarily true. Sometimes bad things happen. So that's how the book kind of throws this all in chapter 5 in memory. Now, you guys are not going to be tested on this until chapter 5 and 6 are not tested till what used to be the final, which is now exam 3. But I've got to get you guys started on this now so you have practice on it before May 15th. So, where is it now? Hold on one second. Here it is. So, here's a really good example we're going to go through, Christian. Have you had time yet to look through chapter 5 at all, Christian?
I was planning on doing it tomorrow.
Okay, yeah, I'm not putting you on the spot of an expectation. I'm just trying to see where I need to, what level to teach at. Okay, so these are very common terms. Mean time to failure are very common terms, okay? So, Christian, have you done any website stuff or server-side stuff?
I haven't.
Okay, so these are, I'm trying to find a base here to use. I apologize. So, but you've used Google, right? You've used search engines, stuff like that, right?
Right.
Okay.
Right.
So imagine if you go to Google, right, and you type in google.com or 8.8.8.8 or whatever, right, and nothing comes up, right? Kind of a bad day, right?
Mm-hmm.
Well, that means they had downtime, right? So the way a lot of these guys calculate that is using these formulas right here, okay, which we'll talk about, all right? And this is why this example's up here is so good. So Google and a lot of these guys, what they like to have is what's called 5 nines, which is operating at 99.999% of the time without any failure time. Bryce, you're probably familiar with this, with what you do there at UCCS. So basically in a single year, that means they have 5.26 minutes of repair time that they do in a year. And the reason why this becomes so important for these large server farms like Google and Amazon is because the total number of customers they're servicing in any instance of time is phenomenal. So when they even with 99%, 99.999% availability, okay, that 0.001% maybe cost them $1 million in lost operating time. It's crazy to think about, but 5.26 minutes would equate to a loss of $1 million of gross income for them. So suddenly these equations become very important, right? So the example here is a pretty good example, right? And this is what I'm going to have you go through with your peers in class. They can have their book open if they want, but I would just like you to present the question, okay, and then work them through it, okay, using the formulas, okay? So it's a bummer this is broken over 2 pages, but whatever. So here's what it says, right? It says some disks are quoted to have a 1,000,000 hour mean time to fail, right? Or it means they wouldn't even have, what's it say? As 1,000,000 hours is 1,114 years, right? Before it fails, it seems like it would never fail. But here's exactly what it's talking about. When you have warehouse scale computers, right, that run 50,000 servers, right, and then you assume each disk has 2 servers, suddenly when you start using these equations, okay, suddenly it becomes very important. All right, so I thought the book did a better job spelling out. They don't, but we'll use it here. So we'll stick with what they do here. I might have to add these into the slideshow. So it says use AFR, right, to calculate how many disks we'd expect to fail per year, which is, this book has a tendency of defining on the fly. So so annual failure rate, okay, so they don't want just an average, they want it annually, so over a year, okay. So if there's 50,000 servers, each with 2 disks, right, how many disks is that server farm hosting?
100,000?
Yeah, 100,000 disks, right? Okay, so I wish it would go to the next page, right? So using annual fail, 1 year, here they put it all out in hours, right? I got to keep moving pictures here to fit everything, right? With 1,000,000 hour mean time to fail means the annual failure rate is 8,760, so they set up the ratio how many hours in a year in order to get the annual failure rate over the mean time to fail. Okay, so they're kind of doing this to create availability, right? But it's inverse of that. Okay, so that means 0.876% will fail. Right. So now with 100,000 disks, like you said, look how many disks will fail per year on average.
Yeah.
So it's pretty substantial. So literally they've got to have someone running around swapping hard drives out almost every day, right? 2 disk failures per day. And that's on an average day. Okay? So yours is going to be a pretty simple one. I'm going to have you walk through this, and then I'm going to have you show them this equation, okay? So when you guys are given questions like this on the exam, what it's going to have to be presented as is you're going to have to be given MTTF or MTTR or MTBF, mean time between failures, and then know how to interchange these. Okay?
Yeah.
There's one more I wish that they'd show here. I'm really tempted to take one from the other book. I'd have to find it, but these are very common, and they're simple equations. They're just operating equations, so they're just ratios. Okay, so do you have any questions on that?
I don't think so. I just need to go over like all the terms and everything,
Okay.
like how what was it? MTBF is equal to MTTF plus MTTR.
Yeah, so let's pull that up, right? Good job.
It's just memorizing everything and then like just switching it out through the formula.
Right, and this is, I'm not trying to throw stones in glass house. It's my class, I'm the instructor. It's just these are some of the things I'm finding out along the way I'd like to update, right? Like this has some parts of what you need, right? The book has the other parts of what you need, and it's like, geez, it'd be nice if they were all in one place. This is just like you told me with the skills4.zip now that you told me about it. I'm like, oh, yeah. Great. So you have dual references. So anyways, I'll work on that. But yeah, at a minimum, they're going to, and y'all are going to be expected to know this and this right here. Because, excuse me, this, right? And this, but these, so that you can properly, depending on what I give you as entry parameters, you can back out what you need, okay? To be honest with you, I really like the way this question in the example is worded in the book, because it gives them a realistic application. So the exam question might be very similar to this. So this is the one I want you to go over in class, is those equations and this example, all right? I prefer you just ask the question, right? And then don't show them the answer and actually calculate it out with them on paper, okay? Kind of like I start asking you, well, okay, how many disks is that, right? Okay, and then how many failures, what percent of failures per year, right? Okay, well, with 100,000 disks, it's that, right? Which, do you understand how they got that?
Yeah. Yeah, I do.
So they just multiplied that out. Why is my calculator not coming up? Oh, it's coming up on my other screen. They just multiplied that out, right? Well, that just screwed everything up. Bringing a calculator over apparently is undesirable when you have split screens and are recording and broadcasting. All right, so so they just multiplied that out. Okay. All right. Any questions on that?
No, I don't think so. It makes a lot of sense.
Okay. Just a note for discussion. They have a pretty good note discussion here, right? So shrinking MTTR can help availability as much as increasing MTTF. So just talking about different ways you can attack this problem, right, to try to get the highest uptime, right, that's available. And so it doesn't talk about in the book, but there's tons of different ways to attack. Oh, here it mentions some ways to attack it. But there's a lot of different ways companies use to attack this problem. So ideally, right, they want to make this 9999999, going forever, as much as possible. Let me see if I want to, yeah. So after you do the example and talk through those, it might be worth just showing this to them, okay? If you have enough time.
Okay.
Okay.
Yeah.
All right. That's it. So because I tried to keep about 15 minutes per problem when I'm teaching each of you guys, we kept right about that. I had to answer the other questions. So that'll be it for tonight. You guys have a great night.
Sounds good. Thank you.
Yep. Bye.